I welcome you for this presentation. In this presentation, we are going to discuss about the RSA algorithm. This is the overview of this presentation. That is introduction to the RSA algorithm, then RSA encryption decryption process, then how to set up the RSA key, then how RSA works, one simple example about the working principles of RSA, then RSA security, under RSA security, the factoring problem, then timing attacks, then chosen plain text attacks, then optimal asymmetric encryption, padding, then summary of this presentation. First is introduction, that is RSA algorithm. How the RSA algorithm was named means the inventor's name was given for this algorithm. That is R stands for Rivest, then S stands for Shamir and A stands for Adleman. So this RSA algorithm was invented by Rivest-Shamir and Adleman of MIT in 1977, and it is the best known and widely used public key scheme because as of now also this RSA algorithm is used in various applications. It is a very famous public key cryptographic algorithm, and this algorithm is based on exponentiation in the Galois field over the integers modulo a prime number. That is, the exponentiation operation is very easy and it takes order of log n power 3 operations are there, and here this RSA algorithm uses the large integers, say for example 1024 bits to 2048 bits. Mostly 1024 bits is used, that is 2 power 16 minus 1, and the security is due to the cost of factoring the large numbers. That is, factorization is a very hard problem in this RSA algorithm. That is, it takes order of e power exponentially. It is exponentially incrementing. So e power log n operations are required, and it is a very hard problem in this RSA. Here we can see the RSA encryption and decryption process. So to encrypt the message M, the sender has to send the message M to the receiver. That is, the sender has to perform encryption and then the sender has to send the ciphertext to the receiver. So in order to perform the encryption process, the sender must needs a message M and the key. That is, the public key is required. So public key consists of E, N. In the next slides, we can see what is E and N. So here E, N is the public key, that is encryption key, and the sender has to compute the value C equal to M power E mod n. That is, here N. In the key generation process, always the sender and receiver has to choose large prime numbers, that is P and Q, two large prime numbers. Then they have to compute the value N equal to P into Q. That is the N value. And with the help of this N value, they have to compute the Euler-Torsion function, that is pi of N. Then they have to choose a E value, that is also a prime number, and with the help of this E and pi of N only, they can compute the value of D, that is the private key. So in the next slide we will be discussing in detail. So here we are having the public key PU is E, N, and the private key PR equal to D, N. This is used for the decryption process. So the decryption process, that is computation, is M equal to C power D mod n. So here we have to note that the message M must be smaller than the modulus N block if needed. So always we have to check this condition whether the message M is smaller than the mod N or not. That always we have to check. So only with that only we have to split it into different blocks. Then we have to apply this RSA algorithm. So this RSA encryption and decryption process is very simple. Only thing is, before performing the encryption and decryption process, we have to generate the key, that is the public key E, N, and the private key D, N. In order to compute N, we have to choose very large prime numbers P and Q. From that, we have to compute the N value. So this is the key RSA key setup process, that is, each user generates a public or private key pair. Here in the public key cryptography, always we have to generate a key pair, that is public and private key. So here what we are doing is, the first step is we are selecting two large prime numbers. This only I already told you that we are selecting two large prime numbers P and Q. Then we are computing the value of n, that is n equal to P into Q. Then we have to compute the Euler-Torsion function. You may remember that pi of n is the Euler-Torsion function. Pi of n equal to P minus 1 into Q minus 1. Then we have to select a random number, the encryption key E. And the value we are choosing must satisfy the condition that E must lies between 1 and the pi of n. Then we have to check the condition that the value E and pi of n must be relatively prime. That is GCD of E comma pi of n equal to 1. Then we are solving the equation to find the decryption key D. That is E into D. Using this formula, we are computing the D value, that is E into D equal to 1 mod pi of n. And here also we have to check the condition that D lies between 0 and n. Then after generating both the encryption as well as decryption key, that is public as well as the private key, we have to publish the keys. That is the public key, encryption key PU equal to E comma n, and we have to keep this private key as a secret word, that is decryption key PR equal to D comma n. So public key PU is known for everyone, but PR equal to D comma n is known to only the receiver. So by knowing the n value, the cryptanalyst can't easily find out the P and Q value. It is not that easy to find out the P and Q value. So how the RSA works? So mainly the RSA works based on Euler's theorem. That is, we know that Euler's theorem, a power pi of n mod n equal to 1, where GCD of a comma n equal to 1. And whatever the steps we have discussed, that already we have discussed, that is in RSA we are applying or using this Euler's theorem, that is we are computing n equal to P into Q, then we are computing pi of n equal to P minus 1 into Q minus 1, then we are carefully choosing E and D to be inverses mod pi of n. That is very important, that E and D are inverses mod pi of n. So we are computing E into D equal to 1 plus K into pi of n for some K. So if you are applying this to this C power D equal to M into E, M power E into D equal to M power 1 plus, for E into D you are having 1 plus K into pi of n. If you apply here, you are getting M power 1 into M power pi of n into K. So we are getting, using the Euler's theorem, a power pi of n mod n equal to 1. So M power 1 into 1 power K, that is M power 1, that is M mod n. So if you are performing operation, then we are getting the message M mod n. So the RSA is working based on the Euler's theorem. So this is a simple example for the key setup process in RSA. So here we are selecting for giving example, here we are using very small prime numbers, but practically if you apply in some critical applications and all, in such cases you have to use very large prime numbers. If you are using very large prime numbers, then only it is providing, the RSA algorithm will provide more security. If you are choosing small numbers, then it is vulnerable, easily vulnerable to attack. So always we have to choose very large prime numbers. So here we are selecting two prime numbers, that is P equal to 17 and Q equal to 11. Then we are computing n equal to P into Q, that is 17 into 11 equal to 187. Then we are computing pi of n, that is P minus 1, that is 17 minus 1 equal to 16, and Q minus 1, 11 minus 1 equal to 10, so that we are getting pi of n value as 160. Then we are choosing or selecting the E value. For finding the E value, we have to know that the GCD of that E value and pi of n must be 1, that is it must be relatively prime. So GCD of E comma 160 equal to 1. So we are choosing E value as 7. Here it is a very small value we are choosing. Then we are determining D, that is D equal to 1 mod 160, that is D always less than 160, the n value. So we are having the value for D as 23. Since 23 into 7 equal to 161 equal to 10 into 160 plus 1. So we are easily find out the value of the D also. After finding out the E value and D value, we have to publish the key. That is the public key PU equal to 7 comma E comma 187. Then the private key PR equal to D comma N, that is 23 comma 187. This way we are publishing the keys. So this way only we are generating the key in RSA. So the encryption and decryption process, so whatever the key we have generated, just apply to that with the message using the formula of the RSA. So here the message M equal to 88 is given. So we have to check always the given number M must be less than N value. So 88 less than 187, that we have to check in the beginning itself, we have to check it. So if it is less means only this algorithm works. So always we have to check it. Then we are performing the encryption process, that is message power E mod N. So 88 power 7 mod 187, that is 11 we are getting. Then with the ciphertext 11, we are performing the decryption operation, that is M equal to 11 power 23 mod 187, that is 88. The same whatever message we are having, the same thing is obtained using this decryption process. So coming to the exponentiation part, so this is the basic algorithm. Steps involved is very simple. The RSA algorithm, first we have to generate the key, then we have to apply it to the encryption as well as the decryption process. So here the exponentiation plays a vital role in the encryption process. C equal to M power E mod N. So the exponentiation. So how to implement this exponentiation means we have to use some square and multiply algorithm is used, so that it is a fast and efficient algorithm for this exponentiation. So this concept is based on repetitively squaring bases here and multiplying the ones that are needed to compute the result. So we have to look at the binary representation of the exponentiation, and it takes order of log to n multiples for the n. So this is one example, 7 power 5. It is given as 7 power 4 into 7 power 1, that is 3 into 7. Always you have to perform the mod operation. 7 power 4 mod 11 you have to apply. So 3, 7 mod 11, that is 7. So you are getting 10 mod 11. So 3 into 7 mod 11 you have to apply, and you are getting the value for this. So next is 3 power 129. This how we can write, that is 3 power 128 into 3 power 1 equal to 5 into 3 equal to 4 mod 11. So this way the exponentiation works in the RSA. So for that we are having an algorithm, that is we are just setting the value C equal to 0 and F equal to 1. Then we are computing, that is for I equal to K down to 0, we are computing C equal to 2 into C. The initial value is 0. Then we are finding here repetitive squaring as well as multiplication we are performing, that is F equal to F into F mod n squaring operation. If bi equal to 1, then C equal to C plus 1, F equal to F into A mod n. So squaring and multiplication operation is performed here, and finally we are returning the value of F. This is a simple algorithm for this exponentiation computation, that is in the implementation process. So this RSA is providing efficient encryption as well as decryption. How it is providing efficient encryption means this encryption uses exponentiation to the power E. So M power E it is using. So hence if E is small, this will be faster. Suppose if you are giving E value as small, the algorithm works fast. But if you are giving E as a very small value, what happens? It is vulnerable to attacks. So in the practical cases, don't use very small E value. Always we have to use somewhat large E values only. Generally, in most of the applications, E is chosen as E equal to 65537, that is 2 power 16 minus 1. And always see choices of E equal to 3 or E equal to 17. But if E is too small means, example E equal to 3, then it is easily it is vulnerable to attack. And mainly Chinese reminder theorem and 3 messages with the different moduli are used here. That is, if E is fixed, we must ensure that GCD of E comma pi of n equal to 1. And if we reject any P or Q, it is not relatively prime to E. So always we have to check the condition that whether pi of n and E is relatively prime or not. That is, GCD of E comma pi of n is equal to 1. That always we have to check. Next is the decryption process. It is also an efficient decryption process. So decryption also uses exponentiation to power d. That is, we are performing m equal to c power d mod n we are using. This is slightly large but insecure if we are not using a large number. Here also we are using the Chinese reminder theorem to compute the mod p and q separately. Then we are combining to get the desired answer. It is approximately 4 times faster than doing directly. So if you are using Chinese reminder theorem, then it is providing fast computation is there. Only owner of the private key who knows values and P of and Q can use this technique, because who can easily find out? Whoever is generating the key. So private key owner only generates the key, because he only knows the method. So he just generate the keys and he publishes the public key and kept the private key as confidential or secret. So he only knows the values of P and Q also. Next is the key generation process. That is, users of RSA must determine 2 prime numbers at random. That is, P and Q value we are generating at random, and we are selecting either E or D and compute the other. So it is not always the case that always E must be published to public and D has to be kept secret. It is not the case. The reverse is also applicable. So based on our applications, we have to keep the private key for encryption or public key for encryption. So based on the application only it works. And the primes P and Q must not be easily derived from modulus n equal to P into Q. So if we know the value of n, because n is given as a public value only along with the encryption E value. So if anyone knows the n value, it is not that easy to derive this P and Q value, means sufficiently large. If it is sufficiently large, it is not that easy. But it is a small value, the cryptanalyst or opponent can easily find the value by using some guess and some probabilistic test. The attacker can easily find out. So the exponents as E, D or inverses. So we have to use the inverse algorithm to compute the other one. So coming to the RSA security, there are possible approaches for attacking RSA, or brute force search is also possible, but infeasible given size of numbers, based on the number size. That is, if you are using very large numbers, then it is brute force search is not that easy. Then mathematical attacks also, here the difficulty is on computing the pi of n value by factoring the modulus n. Because if the n value is anyway known, it is a public value only, but factoring P and Q is not that easy. So mathematical attack. Then timing attacks on by running on the decryption process. This timing attacks, it is vulnerable to some timing attacks. So researchers are proposing some improvement over the RSA to provide to avoid the timing attacks. Next is chosen ciphertext attacks. That is based on the ciphertext. One of the properties of RSA, it is vulnerable to this chosen ciphertext attack. So what the researchers are suggesting means they have to pad some values in the plain text in order to overcome this chosen ciphertext attacks. That is one property. So based on the block of the RSA, it is vulnerable to chosen block size of the message. It is vulnerable to chosen ciphertext attacks. So the researchers are proposing some methodology to overcome that. So here main thing is the factoring problem. Factoring problem means here the mathematical approach takes 3 forms. That is, we have to factor n equal to P into Q. Hence we have to compute pi of n. Then we have to find out the D value. That is determining pi of n directly, and we are computing the D value. So we are finding the D value also directly. But currently, everyone is believing that all equivalent to factoring. That is, there are slow improvements over the years. That is, as of May 05, best is 200 decimal digits. That is 663 bit with the least significant bit is given. That is, least sieve is given. And the biggest improvements come from the agreement is they have given some quadratic sieve to this GNFS sieve, then to LC. They have given that. Then currently they are assuming 1024 to 2048 bit RSA is secure here. So generally they have choosing the block size as 1024 bit and 2048 bit. That is very, very important, that they are ensuring that a P comma Q of similar size and matching the other constraints here. That is, this is the factoring problem. So another thing is timing attacks. So this was developed by Paul Kocher in mid 1990s. It is just like a burglar timing things only. That is on which time, in what operation, that is at the time of decryption, whether it is possible to perform some attack or not. Likewise, the attacker is finding the trying to exploit or finding the vulnerabilities in this algorithm. That is whether we are multiplying by a small number or large number. So depends on all the numbers only. Initial factors are varying, which instructions we are executing, all those things are depend. So we are inferring the operand size based on the time taken to compute, because if you are using large numbers, then what happens, it takes more time, but if you are using small numbers, it takes small time. So based on that, the attacker is thinking that he can easily think that or guess that here only if it is taking small time, then he used to guess that only small numbers are used. So whatever the prime numbers, small prime numbers available, he will guess all those numbers. But if it is taking long time, then only the attacker will think that long numbers are used. So based on the timing or number of time taken to execute the algorithm, based on that they are performing some attacks. So in order to overcome that, some measures are given. That is, some researchers are using constant exponentiation time. Then they are adding some random delays. Then they are adding some blind values in the calculations. So these are some of the measures to overcome the timing attacks. Next is the chosen ciphertext attacks. This RSA is vulnerable to chosen ciphertext attacks, and the attackers choose ciphertext and gets the decrypted the plain text back. That is, they are choosing the ciphertext to exploit properties of RSA to provide information to help the crypt analysis. So this can be countered with the random pad of plain text. For that only, researchers suggest one methodology called optimal asymmetric encryption padding. So here what they are doing is this P is the encoding parameter and the seed is the seed value that we know. Then what message is the message value to be encoded. So in the message value we are padding some values. So at the end of the message we are padding some value. Then we are computing the this message. We are padding something. Then we are padding from the plain text that is encoding parameters. We are generating the hashed encoding of the parameter and we are attaching that. So we are getting the data block. So how we are having the data block means, whatever we are doing, we are having the message m is there. So here we are having the message m. This is the original message. Then we are performing some padding operation. Then we are using the encoding parameters. Then we are finding the hashed value of the encoding parameters. That is also appended here. So we are getting the data block with a combination of message, then padding, and the hashed value of the encoded parameter. Then what we are applying with the help of this seed, we are getting the mask generating function. This mask generating function is XORed with the data block to get the masked data block. Then again with the help of the seed, we are XORing the seed with the mask generator function, and the output of the mask DP is passed and the mask generating function is XORed and we are getting the masked seed. That masked seed and the masked data block is given for the encoded message. So this way we are performing some modifications. Before applying the RSA algorithm itself, we are performing some modification, or we are padding something to the message and we are performing the encryption process in order to overcome the chosen ciphertext attacks in this RSA. So in this presentation, we have discussed about introduction to RSA, then RSA encryption and decryption process, then how the key is set up in RSA, then how the RSA is working. It is working based on Euler's theorem. Then we have seen on example how to generate the key and how to perform encryption and decryption. Then we have discussed about the RSA security in terms of factoring, then timing attacks, then chosen ciphertext attacks. And to avoid the chosen ciphertext attacks, we are having the optimal asymmetric encryption padding. RSA is a very important public key cryptographic algorithm, and it is used in all applications, like in order to provide authentication, that is digital signatures, then to provide confidentiality, then both the confidentiality and authentication. So in all the cases, this RSA algorithm is used. So it's a very important algorithm, and you please go through your textbook. This public key cryptography and this RSA algorithm is available in chapter 9 in your William Starling's 7th edition textbook. Please go through chapter 9 for more details about RSA algorithm, and please solve the book back problems given in chapter 9. Thank you.